I just want to tell if there is some specific topic that you want me to cover, then let me know after this lecture. We will cover in next class. Okay, so welcome everyone in NPTEL GATE Physics classes. So today we are going to learn the concept of method of images, and it is a part of electrostatics. Mainly, we are going to use this method of images to calculate electric field and electric potential. So let's start it here. My screen visible to all.
Yes, ma'am.
Yes, ma'am.
Okay. So generally, what happens is if you have a charge in case of electric field and you wanted to calculate what is the electric field at a certain distance r, you can just simply use Coulomb's law to calculate electric field and potential. So if there is certain condition that will change, then you cannot use this thing. For example, if you have a charge q and a ground conducting plate is placed near to this charge q, then if you wanted to calculate the electric field and potential due to this charge q anywhere in this plane, then the simple Coulomb's law will not give you the correct answer, because if you have this conducting place, so the property of conductor is that if you place a charge near to that conductor, it will try to pull out that negative charges. So they will start kind of moving onto this surface. So we just wanted to calculate what is the field and potential due to this charge distribution anywhere in this region. So the charge that is induces by this positive charge onto the surface also going to affect here. So the electric field and potential will get changed due to this. So we wanted to calculate what is the electric field and potential when you have a charge distribution near to this conducting ground conducting plate. It could be grounded or it could be given some another charge, V0, something like that. We will see how to handle this one in this case also. So you will understand this thing. We have a ground conducting plate and a positive charge is placed. It will induce certain charges on the surface of this plate, and due to which the electric and field and potential will get changed into this region, and we wanted to calculate what is that electric field and potential. So the if you try to see this from mathematical point of view, if this is your z-axis, then at z equals to 0 plane, you have the potential which is 0. And at a very large distance, you already know that the potential is inversely proportional to R. So at a large distance, your potential V is going to 0. So we have two boundary conditions here. V equals to 0 at z equals to 0 and V tending to 0 as the distance will become very large. If we create some another system which is not exactly like this system, but something different, but this condition is again created by another system, then we can solve for that system for electric and field and potential. That will become our problem easy. For example, if I consider that this is of some surface, it is not a conducting surface, obviously. It's just some surface here, and we give a positive charge Q and a negative uh, positive charge Q, and we want the potential V to be 0 at this Z equals to 0 plane. So what we do is we place another charge minus Q at this same distance, so that potential at this surface will become 0. So we place minus Q charge just to make the potential 0 at this surface. So this condition, which is originally in this case, will then be available with these conditions. And obviously, the charge potential due to a charge is given by q upon 4 pi epsilon naught into distance d. So at the distance we become too large, so potential will tendings to 0. So both the condition which is originally from this case now available with this case. Since we do not know what is the induced charge here, so we cannot calculate the electric field and potential here. But we know already that what is the charge is here, so we can calculate what is the electric and potential, electric field and potential. So this condition will become much easier to solve, and it will give exactly the same answer as we will get in this case. So basically method of images is just try to create exactly the same boundary conditions that is available to us with ground conducting plate here. We will see that the minus q charge is again can be calculated, that the minus q charge is calculated from these boundary conditions too. So we will solve this problem. Instead of solving the tough problem, we will solve easy problem. So the potential is given by q upon 4 pi epsilon naught into distance d. So here, if you wanted to calculate the potential at any other point, so we will calculate, for example, this is the point P at which I wanted to calculate my potential. It is at some distance r, which is in xy coordinate can be written as square root of x square plus y square plus z square. But since in z direction, my charge q is displaced by d, so this is the position of first charge, and minus q charge is taken extra. So this is the position of second charge. So this is the potential for this configuration. And the condition v equals to 0 at z equals to 0 is can be seen here. If you put z equals to 0, the potential will become 0. And at a distance, when this term, this whole term, r here is just square root of x square, y square plus z square. So as this term become too much large, this term will become 0. So this potential will satisfy exact boundary conditions. Now we wanted to know what is the induced charge that is available on this surface, since that is one of the possible thing which is affecting our potential. So the induced charge can be calculated using minus epsilon naught of gradient of E vector. So this is coming from this, Gauss's law, where electric field is given by sigma upon epsilon naught, and you can always write divergence of electric field as negative gradient of V as sigma upon epsilon naught. So sigma can be written as minus epsilon naught gradient of V. So this is the same definition from which we can calculate the surface charge. And the derivation is if you have a surface in xy plane, then normal to that plane is that direction. So here it is z direction. So we will calculate del v by del z.
Ma'am,
Yes,
can you tell why v equals to 0 when z equals to 0 one more time, please?
this one
You said there are two
from
boundary conditions. The second one I can understand, but why v equals to 0 at z equals to 0? Why not it is
actually.
constant?
Okay, so here we have taken this case that V is equals to 0 for the case of ground conducting plate. This condition we have already taken, but the same problem can be solved for V equals to some constant value. It will not
Oh,
affect your answer.
okay, okay. Grounded.
So
Oh,
with
okay.
it,
Thank you.
yeah, it's grounded. So okay, so we will then differentiate our potential with respect to Z, the this formula, and this, and then we put z equals to 0 since we wanted to calculate what is the charge distribution at the surface of this plate. So when we differentiate it, I think you are all familiar with how to differentiate. So we will just take del by del z of this quantity. So this is the differentiation, and we calculate sigma, which is minus epsilon naught del v by del z at z equals to 0. So sigma will become this value. This, and you can see that the charge that is going to induce is going to be negative. This is obviously if you wanted to put this potential 0 at z equals to 0, so you have equal and opposite charge on the other side. So your charge is negative. And to calculate what is the total charge that is going to induce, you already know that sigma is the surface charge density. That is, it is given by Q upon A. So you can calculate it as sigma into dA. Yeah, is the surface. Yeah, this integral is over a surface. So just to make the calculation simpler, we just put it in polar coordinate where x is given by r cos theta, y is given by r sin theta, and x square plus y square equals to r square. In that polar coordinate, we can write our poten area vector as r dr d theta or d phi. I just take it d phi here. So this will be phi. So this is our sigma vector, sigma surface charge density. So the theta can goes, this phi can goes from 0 to 2 pi inside the integral, and r can goes from 0 to infinity, and we just integrate it. So the total charge that is going to induce is minus q. And this is the same charge that we initially taken, like just to put our potential zero here. So even with this calculation, the charge that is going to induce is going to be equal and opposite to this total charge plus q. So this is the case for the ground conducting plate, but this could also be possible for an even if you have charge distribution, something like you have a plane in which this is ground conducting plate, and you can also place a line charge density with lambda as a line charge density. So you do not have to be point charge q, it could be a continuous charge also. But in that case, on the opposite side, you have to take negative lambda as in induced charge. Now we have to calculate what is the force and energy. See, you have this surface charge and which is given a potential V, and you have another point charge Q. So because of this point charge Q, there is a surface charge which is induces onto this surface, and it is negative of that Q charge. So they are going to be a force of attraction between these two. So we have to calculate what is that force of attraction. And since we can solve this problem by taking plus q minus q charge, which is placed at a distance, 2d. One is d here and one other d is here. So we can just calculate using Coulomb's law. Two charges placed at a distance 2d. So this is going to be your force. So everything is same for this picture and for this picture except the energy. In the first picture, we have, a surface, and this is a conducting plate, P is equals to 0 and another charge Q. And we try to solve this using the similar problem, but we take it as positive charge Q and minus charge Q. The energy of this case is going to be half that of case. So whenever you encounter this question in GATE exam, so this will going to be occur with you that uh, you try to focus that the energy is going to be half. For example, in this case, where we have two charges and there is no conducting plate, you can simply write energy as Q1, Q2. I think you know this formula. Epsilon naught into R is the distance between these two. So distance is 2D, so you can write this. But in case of one charge and a conducting place, it will be half. And why this is half? Because if you look at the first principle, how you calculate the energy in electrostatic case, it is given by epsilon naught by 2 minus infinity to infinity square d tau. D tau is the volume element, E is the electric field. So in this case, we have the integral from minus d to plus d. But in other case, we have the integral from 0 to d. So in the first case, it is going to be twice. However, in this case, it is going to be just one. So your energy will going to be half in this case. So with uh, we can also solve another problem like
Ma'am,
similar. Yes.
ma'am, can you explain one more time why this is half?
Okay. I will explain it. So in this, we have two cases where conducting plate V is equals to is placed at Z equals to 0. And in other case, we have a charge plus Q and a charge minus Q, which are placed at a distance of D and D. So generally, the main formula to calculate the energy is this one. So you take integral from minus infinity to plus infinity. So when you try to calculate the energy in this case, you can just take the integral from, you know, minus d. This is z equals to minus d to z equals to plus d. But in, and you already, I think you know that this integral can be written as twice of 0 to d. And similarly, in this case, then you have a conducting place at z equals to 0. So you have nothing on this side, only z equals to 0 to d. So in the second case, you have 0 to d already in your integral. So this one will create twice of energy compared to this one. So you solve problem using this configuration, but try to make your energy half when you try to write the answer in GATE exam. I think it is clear to you.
Yes, ma'am.
Okay. Similarly, there is this another question that can also solve like that. You do not have to have, conducting ground plate. There can be a conducting sphere also. It could be grounded. I have just take P equals to 0 just to make simple. So you have a charge q which is placed at a distance a from this center of ground conducting sphere, and you wanted to calculate what is the potential in any of this regime. So we have again going to make the similar condition. So for example, if you take these 2 points on this sphere and you just stretch it, you know, this one is stretched in this direction, this one is stretched in this direction. So it will kind of become plane kind of condition. So if you place a charge q here, so minus q you can place to make the potential 0. So that means you have to just place another charge q inside this sphere so that you can make the potential 0. So just to make this condition exactly similar, we have take this configuration. We place a charge q, which is we don't know what will be the charge inside. For a plane case, it is simply minus q, but for a spherical case, it will be little different here. We will find out what is that q dash is. So at a distance, let's say it is placed at a distance b from the center of this sphere, and we wanted to calculate what is the potential at any point v here. So this is your sphere line. So at a distance r from this point q, okay, I think you can see this condition clearly. We have a sphere which make an angle theta. So there is a point P at which we wanted to calculate the potential, which is at a distance r from this charge q and r dash from this charge q dash. And from the center of the sphere, it is at a small distance r. So since this is distance r is going to be fixed, we will write all distances capital R and this small r dash in terms of this small r. So R is given by this formula from cosine's law. For example, if you have this triangle and it makes an angle theta and you want it to calculate, this is R. So you can calculate R as this formula. And R dash is given by, for the case of R dash, we have R dash R and this distance is B. So this is R dash and potential can be given by this formula. So at this surface, we already know that the potential is going to be 0. So at r is small r equals to capital R, it will become surface of this sphere and potential will become 0. We just put this value inside this and we just put it 0, so this term will become 0. And we just take this term on this side. So now we have this condition. This condition is trying to be same, but to make both of these terms in equal footing. I think you are familiar with this concept that whenever you have this condition of 1 by square root of 1 plus, or maybe a square plus something like b square, and a is greater than b. So just to solve it simply, you take a outside of integral and it will become b by a square. So this term is become much less than 1. So you can solve it by approximation as 1 plus b by a square to the power minus 1 by 2. And then you can take an approximation as 1 minus 1 by 2 p by e square approximation. So just larger term we are going to take outside. So to make this term equal footing, we just take the largest term outside of integral. See, R is the radius of this circle. Cap small a is the distance of this charge q from this center of circle. So a is greater than r. B is inside this sphere, so B is going to be smaller than R. So in this integral, A is larger, so we will take A outside. In this integral, R is larger, so we will take R is outside. And now both these two terms will came on equal footing. And when we try to equate on both sides, we equate this charge system. From that, we will find that the charge Q dash is given by minus R by AQ. And when we equate these terms, we will find out that the distance is given by R square by A. So you have a sphere and there is a charge Q. So the charge Q dash is induced at a distance B, which is given by this expression, and the charge Q dash is given by this expression. So we will find out these two terms. From that, we can calculate what is our potential. We just put this value of B and Q dash. Electric field can be calculated by taking negative gradient of V. So it will become just del V by, this one is in spherical polar coordinate, the gradient. So the radial component is given by del V by del R. We differentiate it with respect to R, and the theta component is del V by del theta divided by R. So we just differentiate it with respect to theta, take out R outside. So this will become our electric field, and this is our potential. And we wanted to know what is the force on charge plus Q. This plus Q charge will induces this charge minus Q charges. See your charge Q dash that is induces of negative charge. So there will be attractive force between these two, and it is given by Q1 Coulomb's law. And the distance between them is already given by A minus B. We just put the value of B here and the value of Q dash. So this is our force, and it is negative sign shows that there is attractive force. And what is the induced charge? Induced charge is given by sigma del V by, we have to differentiate our potential. So this term del V by del R is this term. We just have to put small r equals to capital R in this expression. And we have to put the value of B and Q dash. And then multiply by epsilon, that will give you total induced charge on the surface of this sphere on this side. And if you look at this charge density, it is a function of cosine of theta. Theta is some angle. So as your theta is changing, your charge density is changing. For example, at theta equals to 0, at exactly the position in the direction where charge q is placed, you have the maximum charge density. Put just theta equals to 0 here. And at theta equals to 180 degree, which is this side, your charge density is minimum. So your charge density is not constant on this surface. It is going to change it as a function of theta. And it will never be going to be 0 at any point. And now we have to calculate what is the total charge that is going to induce on the sphere. So we just take this sigma, and total charge Q is given by sigma into dA. So dA element in spherical polar coordinate is given by r square sine theta d phi in r cap direction. And at the surface, we can put small r as capital R, theta from 0 to pi and phi 0 to 2 pi. And we just integrate this value of integral by putting this term as some constant and differentiate it. So your total charge Q is going to be QA upon R. And if you look at this total charge Q, this is going to be again the same charge, which is this one. We just calculated it using equating. The same charge is calculated using some more integral process. Okay. So basically, this is how you are going to solve all the problem in method of images. You just have to calculate the potential first. And from that potential, your whole journey of solving of this problem will start. So we will solve the case problem here. That question is from GATE 2011 exam. In this question, it is given that two charges Q and 2Q are placed along the x-axis in front of a grounded infinite conducting plane. So this plate is already grounded, that means potential is zero. They are located respectively at a distance of 0.5 meter and 1.5 meter from the plane. What is the force that is going to act on a charge Q? So we have to calculate the force on charge Q. We already know that to solve this problem, we have to create a similar charge minus Q at a distance of 0.5, and this one is 0.1.5. Another charge 2Q at a distance of 1.5 with negative. So on this charge Q, there is a force due to this charge 2Q and minus Q and minus 2Q. So the force is given by Q1 Q2 upon 4 pi epsilon naught R square. So I think you are not, mm, you know this thing, this Coulomb's law. And 2Q charge is placed at a distance of 1 meter from this charge. So distance is 1 meter for 2Q. This is also 1 meter for minus Q, and for minus 2Q, 1.5 this and 0.5. So this is 2. So the total charge is Q square upon 4 pi epsilon naught into 1 by 2. So this is the correct answer in this question. Similarly, there is this question from GATE 2015 exam. A point charge is placed between two semi-infinite conducting plates which are inclined at an angle of 30 degree with respect to each other. How many images is going to form for this charge? So there is a charge Q is placed here. So there is a very general formula to calculate the number of images. This is generally come in optics when you have two mirror. So you wanted to calculate how many images of certain things is going to be formed. And this is given by 360 by theta. Theta is the angle between these two planes. So this will here given theta is 30. So number of images is going to form is 11. And for a simple case, if theta is 90, let's say you have two conducting plates which are placed at 90 degree to each other. So how many images is going to form? So exactly same distance d, there is a charge minus q from this plate, and exactly same distance d, there is a charge minus q. And this is the distance which is r from this. So r is distance plus q. So total images are 3. So from the formula, the images are again going to be 3. So in the last year, these two questions appeared in GATE exam. I haven't found any other question. If you will find it, then you can comment. I will look into the questions. And if you do not understand anything, just let me know. Okay, so is everything clear? Then we'll
Yes,
Can
ma'am.
you show that sphere formula once again?
for this fair case, this one,
Mm.
the notes is going to be shared with you on this YouTube link. So all the notes are going to be available.
And ma'am, I was having a basic doubt. You said that the charge density is not zero, but if I consider electric field inside that shell, then it will be something. It will come some value. So how can it be?
Can you uh, just repeat your question?
You said that the charge density is not zero anywhere on the sphere.
Yes,
But if I consider electric field inside that sphere, uh,
yes.
it will have some certain value.
So the charge density is distributed such that the total electric field inside is zero. It will become like a case of cavity, in which you just place some charge. So positive charge will induce here, negative charge will induce on this side. So total electric field will become zero. So it's again it's a conducting plane. You cannot have electric field inside this
Okay,
sphere.
means charge at theta equal to 90 is 0.
Theta equals to 90 charge density
Mm-hmm.
is not zero. How can this term will become zero? Other terms will still be there. How can you make this term zero?
Uh, Ma'am, I was saying that it should be symmetrically distributed, right?
Yes.
But it's not coming like that. Means if I integrate this term from theta equal to 0 to 2 pi and d theta, this
Hmm.
sigma term, then it won't come 0.
Sigma can never be zero, na? There is always going to be some charge this is induces. Electric
No,
field
ma'am,
is zero.
I'm saying total charge should be 0.
Total charge, there is this total charge that is going to induce that we are trying to find. We are not trying, uh, means I do not know why you want to make the total charge to be zero. Just
No,
because of
ma'am,
this
I'm
configuration.
just cross verifying it by means it should come 0, right? There can't be any charge.
There is a charge which is induces. In this case, the charge is induces, but if you have another conditions, not in this case, but if you have another conditions of hollow cavity, in that case, you have charge zero. Here, the charge would not be going to zero. See, this charge plus Q is always going to attract some electron, and there is always going to be some charge induces on this surface.
Then that's what I was saying, that charge will be induced on the surface. So there will be some electric field inside it. How can this happen?
Okay, so you want me to draw these electric field lines? Maybe that will clear. I'll try to make this electric field line. They are just hope I will create these lines for you. See, this will be like this. You have a surface and there is a plus charge Q, and electric field lines will go from this charge Q to this surface. They are always going to be away from the charge Q, but outside also this is like that. Inside there appears that there are some electric field lines, but they are not. You can think of it like there is a minus Q charge which is here, so it's kind of attracting these lines. You can think of like that. Yeah, there is some electric field lines just to balance your thing. So this is how the electric field lines appear in this case. I think this is now clear that electric field line is there in this case just to make this complete thing.
But the fictitious charge is acting like real charge then, ma'am. if if it is.
This fictitious charge, yes, it will act like that, but it's just to kind of make your problem much easier to solve. It's nothing in reality like this. You just use it to solve your problem. Even method of
Ma'am,
image is just used to solve your problem. So you are asking something, someone.
ma'am, I think there will always be charge because image charge is actually when you are actually changing the problem to a different problem. If you place in spite of the grounded conducting surface, if you put q prime, then you will get the same equation. So there will always be charge.
So in this condition, the surface of a sphere here has a potential V equals to zero, but it is not conducting. And the problem that we are trying to solve, in that case, the surface is not conducting, and we just try to make the problem, which is the conducting surface, to be much easier, and we solve this using this kind of conditions. So this charge minus q, even the fictitious, but for this problem, this condition is real, but this condition, the charge minus q is not in conducting one case. So we just try to solve this problem using this method. So this charge minus q, even though fictitious, but for this problem, it is real. And the surface here is not conducting.
So
Ma'am,
we
if it.
cannot assume this sphere to be a conducting surface because there's electric field inside the surface.
For this case, yes, we are not consider it as conducting. We are just trying to make the potential to be zero at this surface. The actual problem that is solved is for conducting surfaces, but here the problem is solved using different method. It's just like you are not able to solve this problem in this space, so you go to other space, solve the problem, and get back to your space. It's just a way and it is not always applicable. The method of images is only applicable when you find certain kind of symmetry in your solution, so you can calculate it. Otherwise, it will not going to be help you in all conditions.
Ma'am, so if I put some charge beside some conducting sphere, then the conducting sphere doesn't act as a conducting sphere.
Yeah, if you place some charge near to this conducting sphere, so it will induce some charges onto this surface, and you wanted to calculate what is the effect of this in induces charges nearby area. Your electric field will get changed, your potential will get changed, so everything will get changed. Even if you look at your potential, it will also be a function of theta. See, your potential is also become a function of theta. That means for the case of conducting sphere, your property is that your potential has to be constant throughout the surface. But just by placing a charge cube, your potential will not remain constant. With different theta, you have different value of potential. So yeah, property of this conducting sphere kind of change. Okay, there are some question. I will next time I will be little slowly in teaching. I'm fast today. Okay, sorry for that. Yeah, all PDFs you can get from where you will get this joining link, you will get the recording link. And at the recording link, yeah, you will direct it to YouTube channel and then you can find all these PDF there. You can stop me whenever you are not able to listen clearly. So whenever you not find sound clearly, you can stop me. I don't know for the mock test of physics when NPTEL will start, but you will get the information through email or we will provide you the information. Yeah, this is almost your November will finish, so you are left with December and January. So if you directed your gate preparation from last year questions perspective, for example, just take the last year questions all from a subject-wide perspective. Means like if you take the electromagnetic theory, just take electromagnetic theory and all questions of the electromagnetic theory and start solving them. And if you encounter some problem, then you just start searching where you are lacking in your preparation, boost that topic, and then come back again. So if you directed your preparation topic wise, then you will be able to do much fine in GATE exam. There is one strategy that I have used in my GATE. See, GATE papers sometimes become lengthy if you start solving problem which is tough. So you just see if you are able to solve the problem within 2 to 3 minutes. Do it. If you are not, just leave it. So you are able to do easier question faster, then you can score better. But if you are trying to solve harder question, you are not going to score much. So this is one strategy just will help you to score better. Okay. So is there any topic that you want me to cover? Maybe you are lacking in some topic. How to revise efficiently.
Ma'am.
Ma'am,
Yes.
even if this conducting surface is not earth, then the induced charge, then even then it's true that there will be electric field inside this inside this surface, conducting surface.
If it is not Earth, means
I mean, if this surface is not grounded, even if this surface is not grounded, then
okay,
also
okay.
this conducting surface will not behave as a conductor.
Yes, that condition is also true. If you are given some other potential V equals to V naught, so just you try to make a similar situation for this the condition V equals to V naught. For example, I said that my potential at the surface is V equals to V naught, and V naught I can try it like Q, there is some charge which is placed at the center, and let's say Q upon 4 pi epsilon naught into R square into R. So at the surface, this is the potential. So I can just place a fictitious charge Q here such that it will maintain a potential of V naught. So this is the charge I can place at the center, and so the condition will get changed from potential grounded to the potential some constant V naught. So the same condition is again valid. You can solve the problem exactly the same way.
Ma'am.
Yes.
Ma'am, when we place a charge near the conducting sphere, what our intuition says is that it will spread a charge. Means the side which is close to the surface, which is from in the right hand side near to Q,
Mm,
it will induce
mm,
a negative charge, right?
yes.
And similar for counterbalancing it, positive charge should be induced on the left hand side.
Yes. That is valid for the case if you are trying to solve problem using conducting surface. The problem that you are trying to solve is using the surface which is not conducting.
But I think
Okay.
if as the conducting plate is grounded, that's why the induced charge on the other surface uh, what he said, it will be will go to ground. That's why there will be a net positive charge. So it came to my mind that this is only happen if the surface is grounded. Otherwise, it will not happen.
So you are saying that the positive charge is because you have this grounded and you just put these charges to be zero on the other left side. Is that what you are saying, trying to say?
I mean, if you there's charge q, so there will be induced charge minus q, and the other hand there will be a positive induced charge. The positive induced charge will come to the ground. I- i-
Okay,
i-
I will, if I try to explain you again, the problem is that we have a ground conducting plate and in front of it we place a charge Q. We do not know how the charge is distributed on this surface. We do not know if it is positive or if it is negative. So what we do is we try to solve it using another problem. We create that problem using method of images and we consider a fictitious surface. It is not a conducting surface. And we place a charge Q here and we solve the problem for this charge. So the charge that you are going to and the potential we are trying to make and the surface is zero. So the charge that is induces on this surface is not like equal and opposite on other side to balance everything because this is not a conducting sphere onto which we are trying to solve a problem. It's a normal sphere kind of surface. But your question may be for this case that if you have a charge Q, then positive charge will maybe it will attract more electrons. So it will be here negative charge and positive charge. Is that maybe that thing confuses you just to make your potential zero?
but ma'am, why did you say then the point charge and a grounded conducting sphere? Why did you say conducting?
Okay, because in case of conducting charges, we do not know the distribution. Electrons are free to move everywhere. But if you do not have conducting something like dielectric, they are fixed. In that case, you can say this kind of distribution like positive charge on one side, negative on other side, and this will create a case of bound charges where you have to find what is the bound charges on the surface. So that is encountered in case of dielectric. But in case of conducting, your charges are free to move very rapidly. So you cannot tell where is the charges, how they are distributed. You cannot tell it from intuition perspective in case of conducting. In case of dielectric, you can think of positive charge on that side, negative on that side. So if you wanted me to cover, I will cover the bound charges with dielectric in next class. Then you can see how the placing a charge Q in front of dielectric is going to affect the case compared to the charge Q placed near to the conducting.
But ma'am, what I wanted to say is, if you have a conductor also, a neutral conductor, and you place some charge near it, what will happen is the free electrons, whichever are present, will move to one side. Means it will produce an opposite charge, say positive charge on the other side, right?
Hmm.
So
Okay.
how can it be? Uh, we can just imagine that it has, like you say, it we solve the problem in non-conducting case, but in conducting case also, we can consider it, means we can physically see that there are some charges on this side and some charges on that side.
So in conducting case, for example, if I take a plate and I will give it some potential, then that potential will be going to flow over all the plates. I mean, if I am thinking about some kind of metal rod and I'm giving that the positive charge, then there will be no negative charge on it. Have you seen that thing? That you have a conducting rod and you are giving positive charge, then half of that rod will receive positive and half of the negative. Have you seen that case? In case of conducting, that thing will vary if you have dielectric.
Mhm. Okay.
So, someone asked, what is the most important topic in EMT? So, till now, from my experience of solving gate problems, I have encountered magnetostatic as the topic in from which most of the gate questions ask. You can all encounter 2 to 3 questions in single exam from that topic. So, this one is most important from my perspective. How to revise efficiently? So if you revise it from topic wise, then everything will organize in your mind, and so you can solve a gate question much better. So try to revise topic wise, like one topic, and then finish completely, then start another topic. And if you try to make your 2 to 3 months, whatever left in your preparation, according to topic wise, then that will help you a lot in your gate exam. Okay, I will cover the dialectic topic in next class from the bound charges perspective. Okay, so we will see you. That generally, if you finish topic completely, that you will never forget that. Generally, when I used to prepare for GATE, so I solve the problem and whatever the important point is, for example, formula or anything, I try to write in the separate paper. So I will solve problem and I will simultaneously prepare my formula notes along with this. And in just for a EMT case, it will cover 2 to 3 pages for all the formulas. In EMT, there is no long formula. The formulas are very, very short. You can just write it down whenever you are trying to solve problem in separate paper. So you will never forget whatever you have revised earlier. In journal, in which topic you are encounter long formulas. There are some long formulas in mathematical physics. Otherwise, there is not much. The PDF note is available in the description box of this YouTube link. You will not find it on this Gate website, but you can click the recording link, then you will go there on YouTube, and then you can see that PDF. All the PDF notes are there. For my case, I have created that link for you. Okay, we will meet in next class. Thank you.